whether serving as a reagent in chemical synthesis, an active agent in agricultural chemicals, a building block of polymer production, or a precursor to pharmaceuticals. Its usefulness is widespread. Understanding how it behaves at the molecular level, recognizing the risk involved in its handling, and continuing to improve production and application methods will ensure that dimethylamine remains a valuable tool for science and industry. Its story is one of transformation and utility, built on the simple substitution of hydrogen atoms and extended into the complex network of modern human enterprise. Heptane is a straight-chain hydrocarbon composed of 7 carbon atoms and 16 hydrogen atoms. It is widely used across multiple industries due to its favorable chemical characteristics, particularly its non-polarity and volatility. One of its most well-known roles is as a benchmark in fuel testing, especially in the determination of octane ratings. Because of its tendency to ignite prematurely in engines, heptane serves as the reference compound against which other fuels are compared for knock resistance. Additionally, it finds extensive application as a solvent in laboratories, manufacturing processes, and various industrial sectors. With growing concern over environmental sustainability, however, the applications of heptane's widespread use have come under increasing scrutiny. Chemically, heptane is categorized as a saturated hydrocarbon, meaning all of the bonds between its carbon atoms are single. This makes it relatively stable and less reactive than compounds with double or triple bonds, such as alkenes or alkanes. Though it has a simple linear structure, heptane exists in several isomeric forms. These branched versions differ in how the carbon atoms are arranged, but maintain the same overall chemical formula. Each isomer exhibits slightly different physical properties, which can influence their behavior in industrial or scientific applications. Physically, heptane is a clear, colorless liquid with a boiling point just below 100 degrees Celsius and a melting point near negative 90 degrees Celsius. It is lighter than water, with a density slightly below 7/10 of a gram per cubic centimeter at room temperature. Insoluble in water, it mixes easily with other non-polar substances. These features make it an effective solvent for compounds like oils, fats, and waxes. Its low boiling point means it evaporates quickly, which is advantageous in processes that require rapid drying or the removal of solvents without leaving residue. In fuel research, heptane plays a critical role in determining octane ratings. These ratings measure a fuel's ability to resist premature combustion or knocking in high compression engines. Because heptane ignites easily under compression, it is assigned an octane value of 0. Its counterpart, a highly knock-resistant compound known as isooctane, is given a rating of 100. Blends of these two substances are used as reference fuels to calibrate testing instruments and determine the performance characteristics of chemical gasoline. High-performance engines require fuels with high octane values to operate effectively, and heptane helps define the lower boundary of this scale. Historically, heptane has influenced the development of aviation fuels as well. During the early to mid-20th century, engineers used heptane in combination with other hydrocarbons to experiment with fuel formulations for high altitude aircraft. This research led to the production of fuels that allowed fighter planes to maintain engine power and reliability under extreme conditions. The insights gained through these experiments contributed directly to the aviation fuel standards that remain in place today. Beyond fuel research, heptane serves as a versatile industrial solvent. In organic chemistry laboratories, it is commonly employed during recrystallization, a process used to purify chemical compounds. By dissolving a mixture in warm heptane and allowing it to cool gradually, chemists can separate impurities from the desired product based on their different solubilities. This method is particularly useful in pharmaceutical research where purity is paramount. In the pharmaceutical industry, heptane aids in the synthesis and isolation of various drugs. One example is its use in aspirin production. In one stage of the manufacturing process, heptane helps dissolve intermediates and facilitates the crystallization of the active compound. A case study from a European facility demonstrated that incorporating heptane in the final purification step increased product purity from 95% to over 99%. Because heptane evaporates quickly and leaves minimal residue, it ensures that the final medication meets stringent regulatory standards. Heptane is also widely used in the manufacture of adhesives and sealants. In industries such as shoe production and automotive assembly, fast-drying adhesives are essential for efficient workflow. Heptane's Volatility enables rapid curing, allowing for strong and durable bonds without long wait times. Similarly, in industrial cleaning, heptane serves as a degreasing agent for machinery and engine components. Its ability to dissolve oils without disturbing moisture makes it ideal for cleaning metal surfaces prior to assembly. A case study from Japanese automotive plants highlight the benefits of using heptane as a degreasing solvent. After switching to heptane-based cleaning systems, the plant reported a 30% reduction in degreasing time and improved overall efficiency. Corrosion-related defects also decreased, as heptane did not introduce moisture into the cleaned parts. However, the study also emphasized the importance of strict safety measures due to heptane's flammability. Despite its utility, heptane poses environmental and health risks. It is classified as a volatile organic compound, meaning that it can contribute to air pollution when released into the atmosphere. These compounds interact with nitrogen oxides in the presence of sunlight to produce ground-level ozone, a major component of smog. In areas where industrial emissions are high, this can lead to significant environmental and public health concerns. One incident that drew attention to heptane's environmental impact occurred in Texas, where a refinery spill released over 1,000 gallons of the compound into a nearby waterway. Emergency response teams worked to contain the spill using absorbent materials and mechanical skimmers. However, traces of heptane were detected in the local groundwater for months afterwards, raising concerns about long-term ecological damage. This event prompted the facility to implement more rigorous containment protocols and highlighted the need for better environmental safeguards. In occupational settings, workers who handle heptane must be protected from its vapors, which can cause dizziness, nausea, headache, and respiratory irritation. Prolonged exposure may lead to chronic health issues. In a study published by a professional health association, employees of a chemical plant who were regularly exposed to heptane showed increased rates of respiratory problems compared to their peers.